Okay, let's get started with transition kernels. So I will write something here. Okay? So whenever you get confused, look at here, okay? So x equals little x, y in f is equal to x is in x times y is in f. This is only a special case. General case is x is in x and y is in f should be calculated as x is in x times y is in f given x is in x. X is equal to x. A and B is the probability of A intersection B is the probability of A times probability B given A. Right? Let's say x is discrete and y is a continuous random variable. Okay? We never introduced this notation. I'm just writing it in case you have seen it before. If you haven't seen it before, just don't look at here. Okay? So now comes the abstract framework. Transition kernel. What is a transition kernel? We're going to have two spaces again. So one is E, and the other is G. Here's what a transition kernel does. Tell me your position in the first space. Let's say X. Let's say this is my position in the first space. And here's what the transition kernel tells you. Your probability or measure of landing in F in the second space is KXF. So there is F here. My probability of landing here is KXF. So a transition kernel from the first space into the second is a random measure on the second space. So it's a measure on the second space whose randomness is due to the first space. Of course, this is not a mathematical definition, but it explains what is happening in this picture. So this object K can tell you the probability of landing in the set F if it knows your position in the first space. That's why it is a random measure. If you have randomness in the first space, your probabilities of landing some sets in the second space become also random. So it's not a measure, it's a random measure. What does that mean? If you fix the first variable, it's going to be a measure. If you fix the second variable, it's going to be a random variable. So it's a dual object, a hybrid object. It has two variables. One is a point in the first space. The other is a set in the second space. So let's give the mathematical definition. A function k from E cross script G to R bar plus is called a transition kernel from E into G if 1 for every x in E. So if you fix your x, this is a measure on G. Second, for every f, so now I'm fixing my second variable, x maps to kxf is a measurable function with respect to E and for L R bar plus. Of course, this x is in E, right? Where is it? So this x is in E, and this is just a positive number, including plus infinity. And this is in script G, and this is just a positive number, including plus infinity. So this is a set function, and indeed it is a measure. It has to be a measure. And this, as a function of x for fixed f, okay, freeze the second variable. Now it is a random variable on the space. It's a random variable on the space. And the randomness is due to my position in the first space. Okay? A few more definitions. So there is some classification of random measures or transition kernels. So let me write them here. So further definitions. So when there is a probability measure on E script E, we call a transition kernel a random measure as well. A random measure as well. Okay. More things. So a transition kernel K is called a transition probability kernel. If the measure part is a probability measure. So if k of x and the full set is 1 for every x. For every x, it is called finite if kxg is finite. So you know classification of measures like probability measure, finite measure, sigma finite measure. So if this happens for every fixed x, then you call it a probability kernel, finite kernel, or sigma finite kernel. It is called sigma finite, but now the partition has to be universal for all x if there is a measurable partition G1, G2, etc., such that kxgi is finite for all x and I. So this measurable partition is the same measurable partition for all x. So this is the classification of the measure part of K. And there is also the classification of the measurable part of K, the function part of K, as a function of X. Okay? So a transition kernel is called bounded if supremum kxg, supremum over x. So as a function of x, it's a bounded function. Okay? It is finite. And here I take the largest possible set because for other sets, it's going to hold true automatically because this is the measure part of it, right? So if you have a smaller set, the measure can only decrease. So I just look at the largest possible set, which is G. It is called, let me say, a transition kernel K. Okay? It is called sigma bounded if there is a measurable partition G1, G2, etc., such that supremum k xgi over x is finite for all I. And maybe one final thing, I don't want to erase here, let me write it here, just one more definition. So a transition kernel from a space into itself is called a transition kernel on E script E. So if it's from E to E, we just call it a transition kernel on E. So this is just a bunch of definition. I mean, this part is really just copy-pasting from the definitions about measures, except that in the sigma finite, in the definition of sigma finiteness, you don't have a different partition for every x, but you have a universal partition that works for all x. Okay? That's the requirement. So you need to use the same G1, G2, etc. for every x. And this is like how you call functions bounded or sigma bounded. Well, we don't have sigma boundedness for functions. We just have boundedness for functions, right? So bounded function means what? Its supremum is finite. So, and we use just the largest possible set because among the values of k for different sets, this is the largest. This is the largest. Okay? And sigma boundedness is kind of a way to combine the two natures of K, namely that you need a measurable partition from the second space, and over each set, your function is bounded. Your kernel is bounded. So over each set, your kernel is bounded. So maybe it is not a bounded kernel, but it is sigma bounded. Okay? In other words, you can chop down your second space into some partitions, G1, G2, etc. And over G1, your kernel is bounded. Over G2, your kernel is bounded, etc., etc. This is sigma boundedness. But the important point is here, is the main definition. Okay? This is my position in the first space. If I know my position in the first space, I know with what probability I will land in the set. If I know my position in the first space, I know my probability of landing in the second space. We haven't discussed conditioning yet. You have to wait for chapter 4 to get the connection between that and this. We haven't defined anything about conditioning yet. But if you know something about conditioning, always consider kernels as conditional distributions. Okay? Okay. Is the definition clear? That's a very important definition. It is crucial in understanding pretty much everything that's going to happen in the rest of the course. Okay? So please ask questions if anything is not clear. So just to make sure we understand this concept, I'd like to discuss with you several examples, maybe 4 examples. First, we're going to discuss the simplest possible kernel from a space into itself, okay? It's going to be a transition kernel on E, okay? First example. What is the simplest possible measurable function? What is the simplest possible measurable function? Indicator. What's the simplest possible measure? Dirac. And they're kind of the same thing, right? It's 1 if your point is in your set. It's 0 if your point is not in your set. And we're going to define a kernel in the same way. Okay? So, example. Let's say we have just E script E. And define X with D. Now I'm going to write D here because we have just one space. So this is 1 if X is in D, and 0 otherwise. So what is that? It is the Dirac measure at X, the value at D, or the indicator function of D at X. All the same thing. So I define it for X in D, X in E, and D in script E. So this is called I is called the identity kernel. Identity kernel on E. Why is this a kernel? Of course, we need to check the definition, right? Why is this a kernel? So for fixed X, this is a measure. Indeed, it is the Dirac measure. As a function of D, this is a measure because it is the Dirac measure. For fixed D, as a function of X, it's a measurable function because it is the indicator of a measurable set. So checking the definition of kernel is for free. Because on one hand, it is equal to the Dirac measure. So as a function of the set, it is a measure. As a function of X, it is a measurable function. For fixed X, it is the Dirac measure. For fixed D, it is the indicator. It is a Dirac measure, and it is an indicator. Indicator function. That's why it is a kernel. Dual nature, right? Dual nature. For fixed X, it is a measure. For fixed set, it is a measurable function. Okay. Second example. Let's say now we have two spaces again. So it has this dual structure. It is a measure on the second space and a function on the first space. So let's create an example where we really multiply a function on the first space and a measure on the second space. So let h be a measurable function and lambda a measure on G. Now define kx of f as nothing but h of x times lambda of f. So x is in E and f is in G, script G. It's a very simple way of defining a kernel. You want to have something that is both a measurable function and a measure on different spaces, right? Take a measurable function from the first space, take a measure from the second space, and multiply them. K is a transition kernel from E into G. Well, why? Why is this a kernel? Because if I fix x, this is like 5 times lambda. Of course, if lambda is a measure, 5 times lambda is also a measure. So fix x, this is just like a constant. Constant times measure is a measure. Fix f, now this is like 5 times h. Well, if h is measurable, 5 times h is also measurable. So checking that it is a kernel is very easy, very simple. So fix x, h of x is a constant, times lambda is a measure. Fix f. Now lambda f times h is a measurable function. Let's take E and G as finite sets. Of course, with their power sets. One to D and one to M. And let's say we have a matrix K, Kxy, okay? So X is in E and Y is in G. In other words, this is a matrix of dimension D times M. Let's say it has positive entries. So let K be a matrix. So 1 to D, let me put D equals 4 and M equals 5. So I have K11, K12, K13, K14, K15, K21, K22, K23, K24, K25, K31, K32, and 41, 42, 43, 44, 45. I wrote all the 20 entries. Good job. Okay, so this is K. And these are all positive numbers, okay? So this is going to be my position in the first space. And I should take a set. Let's say this set. That I'd like to land in the second space. So define the probability of, or the measure, whatever, of starting at x, given that we start at x, and land in a set F as kxy, where y is in F, for x in E and F in 2 to G. It's the power set. So for instance, K from 2 to the set 2, 3, 4, 5 is what? K2, 2, K2, 3, K2, 4, K2, 5. This is the probability of landing in the set, given that we start from position 2 in the first space. What does it look like from an undergraduate course? What kind of a matrix can this be? Have you ever calculated such probabilities using matrices? Have you ever seen a probability matrix? Have you ever seen a transition probability matrix? Which topic was that? Markov chains, right? So this can be, for instance, the transition probability matrix of a Markov chain. If you know what a Markov chain is. Of course, this is not something that we have discussed so far. Anyway, so we call K the transition matrix for the transition kernel K. This is a transition kernel. You can check it. So check K is a transition kernel. When is this a transition probability kernel? When is this a transition probability kernel? So the row sums must be equal to 1, right? So if they add up to 1, this becomes a probability measure. So let's write it separately. So if kxy, y in G is 1 for all x in first space, so this is the row sum, right? Then K is a transition probability kernel. And the matrix K, little k, is called its transition probability matrix. So if you deal with finite sets, you don't really need the kernel, but you can just work with its transition matrix, right? The matrix would be enough. But if you have a continuous or a general state space, for the second one, the matrix is not enough. Well, also for the first one, the matrix is not going to be enough. So transition kernels are just extensions of those transition probabilities appearing in elementary contexts such as Markov chains. It is a way to model conditional distributions. Of course, we still don't know what a conditional distribution is in the setting of this course, but we're going to relate them soon, in 2 weeks. Okay, I was going to give one more example, but that is more like a exercise. Let me write it here. It's an exercise. It's going to be a homework exercise. Okay. The reason that it is a homework exercise is that it is not as trivial as those 3 examples. Okay? So let K be a. So now I'm going to mimic this example. I'm going to pass to a function from a matrix, okay? If I have general state spaces, E and G, not finite, I cannot see it as a matrix, but this is nothing but a function, right? Be a measurable function. And let lambda be a measure on the second space. So now define kxf as k little k xy lambda dy over f. So this lambda is, in this example, was just the counting measure on the second space. The counting measure on the second space. So you just look at the sum of the entries of this matrix. Now it's going to be an integral with respect to this measure lambda. Okay? So for every x and for every f in script G. Show that K is a transition kernel. And this little k is called its transition density. Transition density. It's a generalization of this example, okay? Whenever you deal with more abstract measurable spaces, this becomes just an arbitrary function of x and y. To define a kernel, you need the second variable being a set. Therefore, you integrate this function with respect to the second variable using some measure on the second variable, on the second space. Okay? In that example, that measure is the counting measure on the second space. So you just add the entries of the matrix, transition probability matrix. So now it becomes a transition density function. Transition density function, let me say. Okay, very good. Questions? Questions? So do you have some feeling of what the transition kernel is now? So it's not an entirely easy concept. I think it is the most complicated concept because it has a dual nature. So you have to see it from 2 points of view. You have to look at it from 2 different viewpoints. Okay? Fix the first variable, it's a measure. Fix the second variable, it's a measurable function. Okay? So it takes some time to get used to it. But if you know something about conditional distribution, if you remember conditional distributions from undergraduate courses, that might help you to make them more concrete in your minds. From E into G. What can we do with that? Well, number one is that we can fix x and treat it as a measure on G. So what do you do with measures? What do you do with measures? What did we do with measures in the first half of the course? For instance, I can have a measurable function and a measure, and then what do I do with those two? If you have x and you have mu, what do you do with x and mu? You can define the distribution, or simpler, you can just look at the expected value or the integral, right? So whenever you have a measure, you can also take a measurable function and integrate them. So let's do it. So take a measurable function G and look at the integral. So I'm going to denote it as K applied to G as a measure. So what does that mean? I integrate my G with respect to K, the measure part of K. So it's an integral over the second space. And now what I obtain is a function of x. So I write x here. X is fixed, but I have to say that it depends on x. It depends on the choice of my x. So it's the integral of G with respect to K, seeing K as a measure. Okay? Just freeze this And now it is more familiar, right? Just g dk, g dk. But everything depends on x, so I have the dependence on x. Hopefully, this is a measurable function of x. So now I have to see it as a function of x. The end result becomes a function of x. So hopefully, this is the case. Let me write it here as a theorem. So I'm going to continue here with one more thing because we haven't fixed the second variable yet. But let me start writing down our main theorem. Okay? So let K be a transition kernel, etc., etc. So for a measurable function G on the second space, Kg, which is defined on the first space, right? It is defined on the first space, is a measurable function. Of course, with respect to script E, because it is the sigma algebra on E. Let me write it in parentheses. This is what I want. And there is a number 2. So let's cheat. So now we're going to fix the second variable. Let's fix f and treat it, namely k, as a measurable function on E. It's a measurable function on E. This means if I have a measure on E, I can integrate this function with respect to that measure. So take a measure. So we're exactly doing the opposite of what is happening here. Take a measure. Let me call it new from script E to r bar plus, right? And look at the integral. So now I write new k because this is my measure, this is my integrand. So I integrate this with respect to a measure on the first space. So it's an integral over E. And this is for every f that I fixed at the beginning. So now this is a function of a set in the second space. If it's a function of a set, I hope that it's a measure. So that's going to form the second part of my theorem. For a measure nu on E, nu k, which is a set function defined on G, is a measure, but now where? On the second space. And there is actually a combination of the two results. For a measurable function G and a measure nu on E, we have, okay, let me wait. So the idea is, can we combine number 1 and number 2? Because look at number 1, we get a measurable function on the first space. And look at what we have in number 2. A measure on the first space. So this is a function on the first space. And this is a measure on the first space. Can I integrate this with respect to nu? And there is another opportunity. This is a measure on the second space, while this is a measurable function on the second space. So can I integrate this with respect to this measure? Of course we can, but the question is, are the results equal? In other words, if I integrate g with respect to this measure nu k, do we get the same result when we integrate kg with respect to nu? The answer is yes. The answer is yes. This is what number 3 tells. And let me write down what I mean by those. These are double integrals. So this is what? I integrate g with respect to nu k. And here I integrate kg as a function of x with respect to nu. It's a function on the first space, an integral on the first space. But kg itself is an integral, and nu k itself is an integral, so these can be seen as double integrals. Apparently they have the same value. So the order is not important. The order, the way you put the parentheses is not important. So this way you really use the dual nature of k. On one hand, you integrate it with respect to a measure on the first space, and on the other hand, you use it as an integrator, namely as a measure for a function on the second space. And if you do both, you get the same result in the two possible orders. Let's see if we have time to prove it. Well, we have time to prove maybe number 1. Let's prove number 1. Now I will erase this part. Well, for every measurable function, g, we have that kg is also a measurable function. How can we prove it? Well, we can start with simple functions and then pass to limits, right? So step 1, let's say g is a simple function on the second space, right? Simple positive. So I don't tell what these things are, right? These are measurable subsets of g, and these are positive numbers, so that this is a simple positive function. Now what is kg of x? Kg of x is the integral of g with respect to k. And g is the sum of those constant times indicators. Now, for fixed x, this is just an integral with respect to k, right? Just an integral with respect to a measure. And we can use the linearity of integral, right? Linearity. To swap the order and write it as integral of indicator fi kx dy. And what is the integral of the indicator? It is the measure of this set. Now, this is a measurable function of x because k is a kernel measurable in x. And if you have a linear combination of measurable functions, this is also measurable in x. And as step 2, what you can do is to take simple positive functions approaching to g in an increasing manner. So these are simple and positive functions. So by monotone convergence theorem, kg1 is less than kg2, etc., etc., and they converge to kg. So kg is nothing but the limit of kg_n's. And these are measurable by step 1. So the limit is also measurable. So that's the proof of number 1. Well, number 2, it's even easier because we just have to check the definition of a measure, right? So nu k of the empty set is, well, what was nu k? Nu k is defined here. Nu k of empty set. It's kx empty set. Kx empty set. Nu dx. Well, this is 0, so this is 0. And also we need to check countable additivity. So for this we need to take some disjoint sets, right? So what does number 2 say? This is a measure on the second space. So let's take some disjoint sets from the second space. Let G1, G2 be disjoint sets. So nu k, well, I should have said F1, F2 maybe. It's not partition of G. Let me say F1, F2. So nu k at the union of those things is defined as the union, the kernel at the union, integrated with respect to nu. Well, k, when you freeze x, it's a measure. So I can use the countable additivity of k itself. So this is equal to sum of I1 to infinity kx fi nu dx. Then we can use linearity to, no, not linearity, we have infinitely many things. What can we use? What can we use if we have a series? Which theorem do we use? Do you remember one of the convergence results dealing with series? Sum of infinitely many integrals is equal to the integral of the infinite sum. It was the series form of monotone convergence theorem. So let me write mon series. Okay, so I can swap this order. And now this is nu k of fi, right? By definition, this is nu k of fi. And this is what I'd like to show because nu k of union is the sum of nu k's. So this shows countable additivity. And for number 3, I will just say a few hints. Well, the hint is very simple. Just follow the path that we used in number 1. Just try to prove it for simple functions and then take limits. So step 1, prove for simple positive g. And step 2, prove for general g by taking limits. So I really want you to try it at home, okay? Just start with a simple positive function and write down what this is, and see that they are equal. And then let Gn be a sequence of simple positive functions converging to G, which is just arbitrary positive measurable function, and then try to use monotone convergence theorem a few times to get the result in the limit for a general G, okay? Try it at home, okay? That's going to appear in the lecture notes, but before looking at that, just try it yourself. This way you can understand how to write down those integrals in the right way, etc., etc. It's a little bit confusing notation maybe. If this is very new to you, it might be a little bit confusing, but just try it, okay? Just try to write these down concretely for a simple positive g, and you will hopefully get some feeling of it. So let's stop at this point, and next week we're going to prove Fubini's theorem.